Let's have a look at this recent buoyant problem here. So it says a team of engineering students is testing their newly designed raft in the pool where the diving team practices. The raft must hold a 730 kilogram steel cube with edges of length 45 centimeters without sinking. Assume the density of water in the pool is 1,000 kilograms. All right, we got the mass of the cube, we've got its side, which will probably give us the volume, and we've got the density of water there. The students use a crane to gently place the cube on the raft, but accidentally place it off center. The cube remains on the raft for a few moments, and then the raft tilts, causing the cube to slide off and sink to the bottom of the pool. The raft remains floating in the pool. In a coherent paragraph-length response, indicate whether the water level in the pool when the cube is on the bottom of the pool is higher than, lower than, or the same as when the cube is on the raft, and explain your reasoning. For both cases, assume there is no motion of the water, meaning it's not like sloshing around side to side. All right, I think a little picture here will help. So we've got this raft right here floating that way, and then we've got this steel cube that is at first sitting on top of it. I guess I should have used blue for my water. I'll just use green. And they're both floating there. So then it slides off, right? And when it slides off, the raft is still floating, but now the cube is resting down at the bottom of the pool here. So it's down here. Now they want to do it in a paragraph length response, but I'm just going to write some bullet points here to explain what you should be thinking. In this case right here, as it's resting on the raft, the initial water level, here's what we know. We know that the buoyant force is equal to the weight of the raft and the weight of the cube. Why? Because it's floating, right? So they're both floating, so that means whatever the buoyant force is up, it's got to be equal to the force of gravity down. And it's equal to both their weights combined there. So then it slides off, right? So, another point here is we know, let's talk about the displacement here. So remember that Archimedes' principle says that the weight of the water displaced, so the weight of water displaced equals the buoyant force. So right now the weight of the water we're pushing out of the way is equal to the weight of both of those guys. Next point you want to think about is when the cube is on the bottom, down here, we know that the buoyant force is less than the cube's weight on it. Why? Because it's sunk, right? So because it's sunk, the buoyant force on it is now less than it was before. You can think about the raft helped the cube displace a bit more weight. The buoyant force on the raft is still the same. So, but there's less buoyant force on the cube there. And so working from that, less buoyant force means less water displaced. And if less water is displaced, then this water level will drop. It will be lower than before because we're not displacing as much water as we did originally. Next part here, it says the bottom of the pool is 5 meters below the surface of the water. The crane is now used to lift the cube out of the pool. The cube is lifted upward at a slow, constant speed. That's key, right? So that means acceleration is equal to 0, which means our sum of our forces is equal to 0. You should always think of those things tied together instantly in your brain. So all drag forces are negligible. Predict how the force exerted by the crane on the cube when the bottom of the cube is at a depth of 2 meters compares to the force by the crane on the cube when the bottom of the cube is 4 meters. Explain your reasoning. Now, do not let them trick you. You've got to remember that the buoyant force is independent of depth. So you know that answer, and that's basically it. That is all you have to put. There's a tendency you want to think like, oh, the pressure is greater down there, so it's going to have some sort of effect. But just remember this, that the buoyant force is independent of depth. And since, actually, let's go a little bit further just to make it absolutely clear here. The equation that we might want to write here is that the tension is going to be the force of gravity minus the buoyant force. So since the weight's never changing and the buoyant force is never changing, the tension will never change there. Next thing they want is a free body diagram. Might have actually made sense to give you this one first because it would have made that question a little bit easier. So it says on the black square below, which represents the cube, draw and label forces, not components that are exerted on the cube while the crane is lifting it. At the bottom of the cube is lifting and the bottom of the cube is 4 meters below the surface of the water. Each force must be represented by a distinct arrow starting on and pointing away from the black square. The lengths of the arrow should demonstrate the net force on the cube. Okay, so I'm just going to draw here, let's say, the tension up like that. And then we've got another force up right here, the buoyant force. Now, you don't know yet which is bigger. That's not super critical. And then it's going at a constant speed, remember, so the net force is 0. So I have one 2 square force and one 1 square force, so a total of 3 squares up. So that means my downward force has to balance them both together, so the force of gravity should be these two added together there. We're going to use this to solve our next one too, this picture here. So it says calculate the force exerted by the crane on the cube. So in other words, the tension when the bottom of the cube is 4 meters below the surface of the water. So we can see that the tension has got to equal the force of gravity minus the buoyant force here. So let's start to find some of these and plug them in. So the force of gravity on this thing is simply going to be 7,300 newtons. We know that because it's a 730 kilogram cube. So what about the buoyant force? We're going to have to find that. So the buoyant force, remember, is the density of the fluid you're in times the volume of the fluid displaced times gravity. So we can find this pretty easily. We're in water, so that is 1,000 kilograms per cubic meter for the density. The volume, they said it's a cube, and they gave us the side. The side is 45 centimeters, so 0.45 meters. Don't forget to cube it. We haven't done that a whole lot yet in this course. And then the gravity is 10. So when you multiply all of that out, you get 911.25 is the buoyant force. So now we're ready to plug back into this equation here. So our tension then will be our weight minus our buoyant force. So 7,300 newtons minus 911.25 newtons. And so that will give us a total of about 6,388.775, newtons.